All right, Chapter 9, Section 2, Special Right Triangles. As the name implies, we're going to talk about a couple of unique cases of right triangles that are going to have some unique properties attached to them. Now, triangles in general, just to back off into our broadest sense here of what a triangle is just simply a three-sided figure, and as such, it's going to have three internal angles. A right triangle implies that one of those angles is going to equal exactly 90 degrees. Now, all triangles, regardless if they're right, acute, obtuse, whatever, all three of their angles need to add up to 180 degrees. That's called the Triangle Sum Theorem, and that's still true. That still applies to all triangles. Right triangles, since one of them has to be designated as 90 degrees, the other two angles would have to add up to 180 paired up with that 90. And so if I have 90 degrees dedicated to one right angle, the other two angles have 90 degrees left to split amongst the other two. And that can be split up in any way, shape, or form. As long as one of the angles is 90 degrees, it's a right triangle. So in this section, we're going to look at two of those unique pairings and look at the properties attached to them. Now, because these are still right triangles, Section 1's topic of the Pythagorean Theorem is still going to apply. A squared plus b squared will still equal c squared, where c is the hypotenuse of that triangle. These are still going to be right triangles. That Pythagorean theorem is still going to apply. And because of the Pythagorean theorem that relates the three sides of a right triangle, you're going to end up with a relationship, a fundamental relationship between each of the sides of this right triangle. And these relationships are going to be expressed in the properties we're going to see here in this section. So the first special right triangle we're going to talk about, and there are two. So the first of the two we're going to talk about is the 45-45-90 triangle, also known as the right isosceles triangle. So the very first thing I want you to take note of here is that if you were to add up 45, 45, and 90, you're going to get 180 degrees. That same rule about triangles in general with the Triangle Sum Theorem still applies. None of these other previous rules break. Okay, so I still have this 180 degree sum total on the inside. The other thing I want you to notice is that the 45 and 45 equal each other, right? Pretty obvious right here. And that's where we're going to get this term of isosceles. Now, isosceles will be familiar to you from previous math courses. There were really two things that were attached with the name of isosceles, and they're both really closely related. First off, the one that we probably most readily associate with this one is that an isosceles triangle has at least two congruent sides. And the same thing is going to be true here. We usually associate side length. I have two congruent sides, whatever the length is, it has to match one other side in the triangle, at least one other side. Now, the other one that's attached to it has to do with angles. Well, if I have two congruent sides, that means I have two congruent angles. And that, in this case, that's the 45 and the 45. And what we learned with isosceles triangles in Math 1, what was probably introduced way back in middle school, was that the relationship between an angle and the side length that is opposite it is very, very closely related. The bigger the angle, the longer the side opposite, right? So for instance, if you were to kind of use this picture of the triangle right here, if I were to say widen these legs, the side opposite would expand. It would make it longer. If I were to take these sides and pinch them in closer, it would reduce the sides, the side length, the side opposite. Okay, there's that relationship that happens. And because of that, we find the relationship that like, okay, well, if two of the angles equal each other, then the side lengths opposite them must also equal each other. And that's where we get this relationship with isosceles triangles. So how does that apply here? So here's where I'm going to talk about this little ratio here, the AA square root of 2A relationship. This is the ratio that is created with this specific right triangle, the 45-45-90. So here's where, again, I'm going to reference our Pythagorean theorem from section 1. It still applies. It's a right triangle, so a squared plus b squared equals c squared. Well, in this case, because it's an isosceles triangle, a and b technically equal the same thing. So if I were to instead say, instead of a squared plus b squared, as if they're two different things, a squared plus a squared, because again, they're the same length, then I can combine those like terms to get 2a squared. And if that 2a squared is equal to the hypotenuse squared on the opposite side, I can take the square root of that. And that's where I'm going to get back to this relationship here. So again, this is unique to a 45-45-90 triangle. Because of the 45 and the 45, the legs have to be congruent to each other. Whatever A is, whatever length this side is, it's going to be matched here. And because of that, using Pythagorean theorem, I can back off to the point that the hypotenuse is going to be some multiple of that same value of square root of 2. Now, square root of 2 is an actual number. If you do that in a calculator, it comes out to like 1.414, yada, 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 yada. Okay, it's a long decimal. It's called an irrational number, but for the record, it is an actual number, right? So if we call it like 1.4, essentially this square root of 2, this 1.4 is multiplied by whatever length this is. And for the record, that makes sense because this side should fundamentally be longer than this one. Why? Because the hypotenuse is opposite the largest of the three angles. And in a triangle, if there's a 90-degree angle, that will be the largest of the three angles. So the side opposite it, which we call the hypotenuse, will have to be the longest of the three sides of the triangle. In this case, it's the longest by a factor of square root of 2, which again is an actual number. It's a 1.4, yada, yada, yada. But that's how we can find it. Because of this relationship, we're going to explore the properties with that. This ratio has to exist. We call the ratio 1:1 to radical 2, or 1:1 to square root of 2, meaning that these two sides have a 1:1 ratio. In other words, they match, they're congruent, they're the same length. And this one is a multiple of square root of 2 times whatever that value would be. All right, so let's see this in example form. So in the notes, I give you two examples because it kind of depends on what information we're given, but you'll be asked to solve for a variable, an unknown, given a diagram. So in this case, we're given a triangle, and more specifically, we are given a right triangle. There's my 90-degree angle, meaning this one has to be the hypotenuse. And then we're given a little bit of information about the side lengths. We're told that this side is 8 units long, and this is an unknown. I'm going to be asked to solve for the hypotenuse in this one. And then I'm told that this angle here is 45 degrees. So for the record, just a couple things to point out. First off, because I know these two angles, this one's 90, this one's 45, it's actually going to lock in and force what this angle has to be, because there's only so many degrees left in 180. In this case, it's going to end up being 45 again, right? Because 45 and 45 make 90. 90 between these two guys plus 90 will give me the 180 required in this triangle. So this is just another way to be told that this is a 45, 45, 90 triangle. And because of that, that's going to force this leg, this 8-unit long leg right here, to match this one. So this, just based on the fact that I was told this was 45 degrees, that's going to force this side length here to also be 8 units long. Okay. So that's going to be the 8, 8, and then I'm going to be asked to find this length here. So I'm going to show you a technique that I use to solve this. This is how I follow those ratios. So as I kind of showed you in the diagram in our notes, each of these legs have to be matching, and I called that variable A. So 8 is equal to A here. And for the record, 8 is also on this side. A equals that side as well. It's just I don't need that information now because I already know what A equals. And then this one, the hypotenuse, is going to be the square root of 2 times A. Okay, so I know two pieces of information here. I know that A equals 8, and that the square root of 2 times A is my unknown. This is the piece I'm going to be solving for. So because of this situation, now I can apply substitution. Essentially, I know A equals 8, so these two are interchangeable. Well, there's an A right there, so I can replace that A with that 8. So this is going to be the same thing as taking that square root of 2 and multiplying it times that 8-unit side length. This will give me my result of x. Just to kind of typically put it in the math order that you'll be seeing this. Anytime I have a radical, I would technically put that second. So this is technically my right answer right here, but just to reorder it, 8 times the square root of 2 is x. This is what we would call the exact solution. Okay, now if in big ideas or on a test I asked you to say round to the nearest tenth, this can be done on a calculator. So in this case, I would first find the square root of 2, which again, as I said, is like 1.4, yada, 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 right? An actual number here. And now I would multiply it by that 8. So times 8 gives me about 11.3. Again, if I had to round to the nearest tenth, which is the first decimal spot, 11.3, about 11.3 units would be x here. Okay, and this is the exact solution, 8 times radical 2. this is what it would be when I like round off parts of the decimal. So let's just do a little sanity check. Let's make sure that makes sense. All right, so, okay, great. We found out that x is about 11.3. Looking back at our diagram, does that make sense? So as I said at the beginning of this lesson, this hypotenuse should be the longest of the three sides. Well, if that side's 8, and this is an isosceles right triangle forcing this side to also be 8, and I found that this one is 11.3, it would be officially the longest of the three sides. So it looks like it checks out math-wise. If you did it incorrectly, where maybe you did the wrong operation and like put stuff in the wrong places, you might end up with a smaller number, and that's a quick like heads up that you should probably redo the problem. All right, so let's do another one that's similar to this. Similar, but it's going to ask you for or give you different information. All right, so part B for our first example here in our notes, you're given a different triangle, a different right triangle, different 45, 45, 90. Okay, as shown here by this right angle. All right, and then we're told that now the hypotenuse, the side opposite 90 degrees, is 8 units long, and that we're trying to solve for x. And they give us in this diagram x in two different places. They do this on purpose. Notice that in this triangle, they didn't tell us anything about either of these angles right here, which would mean that they're unknown. I know that this one's 90, as given by that box, meaning there's 90 degrees left to split up between these two. And here's where they give me the hint. This side length is an unknown. It's x units long, but it's matched here, meaning whatever x equals here is matched over here, which means that this is an isosceles triangle. These two side lengths here need to match. What does that mean? Because these are congruent side lengths, that's going to force these to be congruent angles, meaning these have to be 45 and 45. That's why we're going to get this 45, 45, 90 situation here. It's just a different way to present it. The massive hint here as you're working through the assignment is that in this part, they're all 45, 45, 90 for these examples we're doing right now. So it's kind of the dead giveaway. And you'll see that there's a distinct difference from the ones we do after this. But anyway, I'm going to end up with the same situation. Both these side lengths are going to be my A value. All right, and technically it's the same thing over here. Both of these are the same side length. They're going to end up being congruent as they are matched. And then the hypotenuse is still the square root of 2 times A. So again, I know two pieces of information. I know that A equals X. I don't need to write it again over here. It's the same thing. And then I know that the square root of 2 times A is equal to 8. So again, I'll use substitution. I know A is X, so I'll replace that A with X. So I'm going to get square root of 2 times X equals 8. And here's where you can see the difference from the last problem. In the last problem, I literally just had to do whatever calculation was over here on the side. In this case, I now need to move stuff away from the variable. So in this case, this square root of 2 is multiplied by X. So I'm going to divide it to the other side. And here's where it's going to get a little tricky. We're going to reference something from a previous unit. So if I divide both sides by the square root of 2, I get this result. Again, square root of 2 is an actual number. Even if it's a long decimal, I'm going to wait to approximate this until afterwards, because at this point, I'm going to use a technique called rationalization. If you recall from a previous unit, it's what we're not allowed to have is a radical or a root here in the denominator. So how do we get rid of it? This is a procedure called rationalization. What I'm simply going to do here is I'm going to multiply by whatever that denominator is by itself in numerator and denominator form. So what am I doing here? What I want you to notice here is that this, I have the same thing in the numerator as I do in the denominator, meaning that this fraction would actually reduce down to 1. Anything over itself reduces down to 1. That's important because when I'm multiplying this, I'm just multiplying this randomly in here, it seems, but I'm multiplying it by 1, meaning I'm not changing any values here. Okay, I'm not fundamentally changing some result, but what I am doing is I'm going to be getting rid of the radical in the denominator. Let me show you what I mean. So anytime I have a fraction multiplied by another fraction, I go numerator times numerator, denominator times denominator. So let's see what happens there. So x is going to equal, in the numerator, 8 times that radical 2. This will look very familiar from the last result. Okay, but now in the denominator, I have radical 2 times radical 2. Now, if you recall the property that we dealt with when it came to radicals in the previous unit, anytime I have a radical times another radical, I can just multiply what's underneath and put it back onto the radical. So that 2 times 2 gives me 4. Okay, so what? I still have a radical in the denominator. That's a problem. But the reason I did this is because this is something I can actually solve. The square root of 4 gives me 2. And whatever ends up underneath my radical, in this case, the whole reason I multiply by this is that what's going to happen is I'm going to end up canceling this radical. See here, watch what happens. So I have 8 radical 2 still in the numerator. In the denominator, the reason I went through that, showing you that like the 2 times 2 gives me this 4 is because this part I can solve. The square root of 4 is actually 2. But what I want you to see as the punchline here is that anytime I multiply a radical by itself, the radical just goes away. It's a way to cancel it out, and I'm left with whatever was underneath that hat. Okay, so that's a way how I can rationalize this. And now at this point, these two pieces here can reduce. 2 goes into both top and bottom. And so the actual final result here would be as follows. 2 goes into 8 4 times. Doesn't do anything with that radical. I can't reduce anything here for the record because that's a radical and this one is not. But 2 goes into the bottom. I already did 2 into the 8. That gave me 4. 2 goes into the bottom once. And instead of putting it over 1, I'll just leave it as it is, meaning this is my final result. Now, had it asked me to round to the nearest tenth, for the record, I would do this on a calculator. I would start with the square root of 2, which is 1.4, yada, 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 and then multiply by that 4 in front, which would give me about 5.7. So another way I could write this, if it asked me to round to the nearest tenth, would be x is about 5.7 units. All right, so let's just double check that sanity here at the beginning. If I scroll back all the way to the top up here, if x, as we solved, came out to about 5.7 units, again, what fundamentally should happen in this triangle, my hypotenuse should be the longest side length in this triangle. As you see here, the hypotenuse is 8 units long. I just found out that x was 5.7 approximately. That does make sense that this should be shorter than the hypotenuse. So that tracks. All right, so those are our examples regarding the 45, 45, 90 triangle, the right isosceles triangle. So let's take a look at the second of these special triangles. The second of these special triangles, the other one that we're going to deal with, is called the 30, 60, 90 triangle. Again, fundamentally, I want you to notice a couple of things right off the bat. First off, that if I were to add 30 plus 60 plus 90, I'll still get 180 degrees. So fundamentally, I'm still following that triangle sum theorem. Okay, that applies to all triangles, whether or not it's a right triangle. The fact that there is a 90-degree angle just means it's a right triangle specifically. Okay, so that's still applying here. And because it's still a right triangle, because that 90 is there, it still has to follow a squared plus b squared equals c squared. Okay, now the reason why this is considered another special one is because it has another unique relationship with the ratio of its sides. So again, we'll notice that there is an A in each of these sides. Again, where A and B, what would normally be A and B here for a right triangle, and this would be C. In this case, there is a fundamental relationship between the three. So let me walk through it. So before I get into describing what each of these has with relationship to the other, let me first talk about the angles involved. All right, so there's a reason why the side opposite the 90-degree angle, the hypotenuse specifically, has to be the longest, because the 90 degrees is the largest of the combination. And no matter what other combination would happen with the other two, 90 degrees would always be the biggest, meaning that the side opposite the 90 degrees would always have to be the longest. Now let's look at these two. This is something that is unique to this triangle that didn't happen in the last one. In the last one, the 45, 45, 90 triangle, because the 45 and 45 equaled each other, it had to have the sides opposite those 45s also equal in length. That's why we had an isosceles triangle last time. These two are not equally to each other. So I will fundamentally not have an isosceles triangle here. But what does that mean? So if I just look at these two angles, the 60 and the 30, positioned here and here respectively, right? The 60 and the 30, 60 is obviously bigger than 30. So the side opposite the 60 should be bigger than the side opposite the 30. Okay. And again, both of these guys should be less than the hypotenuse. Now, this is one of the parts that gets a lot of people confused. So bear with me here. All right. So the side opposite the 30, which should be the shortest of the three sides, I'm going to designate that one just regular A. Okay. Again, just designating it some value. So again, this will have some side length, whatever it is. Okay, however many units, however long, large, small, it doesn't matter. It'll have some side length. We'll call that one A. Unique to the 30, 60, 90 triangle is whatever value that is, take that value and double it in length. That's going to give you the hypotenuse. Unique to the 30, 60, 90 triangle. So again, whatever value A is, in this case, the side that's opposite the smallest angle, the 30 degrees, whatever length that is, take that length and double it. That's why I say 2 times A for the hypotenuse. So how do these relate to the other side here, the one that's opposite the 60? Now, fundamentally, again, the side opposite the 30 degrees has to be the shortest side because it's the smallest of the 3 angles. 60 is bigger, so this length has to be bigger. So that's why I have some multiplier here, but it still has to be smaller than the double length. Okay. And so in this case, if we were to go back to Pythagorean theorem, we would actually get to the punchline here that this side opposite the 60-degree angle is the square root of 3, which again is an actual number. And if I were to do that in a calculator, it comes out to about 1.7, the square root of 3. Okay, so it is an actual number. It's a long decimal, but we'll get back to that. Right, so at 1.7-ish plus a lot of other decimals and stuff times whatever that original length is, that will give me the extended length here. But also notice that, again, if I were to take the square root of 3, it's about 1.7-ish. And the reason why I bring that up again here, because this ratio of 1 to 2 to radical 3, a lot of people think that the radical 3 will be the biggest number here because there's a 3. It seems like 3 is bigger than 2. But again, the square root of 3 is a different value than 3. 3 is 3. The square root of 3 is about 1.7. It's basically answering the question, what times itself will result in 3? But in any case, the ratios, again, are about a 1 to 2. So that doubles in length here. But this one's about 1.7-ish. And again, the exact solution here would be the square root of 3. So where does that come from? Okay, it's not made up. It's not random. So again, if I go to a squared plus b squared equals c squared here in the margin, this is just proving where that ratio comes from. Again, here, if I had the a value just designated as itself and the square root of 3 times a as b, and I were to square both of them together, yeah, I'll let you kind of explore where that comes from. But essentially, that square root of 3 turns into 3 when I square it. And a squared plus 3a squared gives me 4a squared. And when I take the square root of 4a squared, the square root of 4 gives me the 2, square root of a squared gives me a. So that's where the double comes from. So that's where it can be confirmed. That's just where it comes from. You're not going to be tested on that. I just wanted to point it out. Okay. So what do we do with this case? All right. I'm going to walk through one example here. I'll let you check the other of the two in the solution. So I'm going to focus on this guy here because it has 2 variables. I just wanted to present to you on the whiteboard to show you what's going to change. It's really the same technique as that first special triangle, but it's going to get down to, just knowing the difference between your ratios, because this one is not isosceles. So in this case, we're given the following right triangle. This one's going to be a 30, 60, 90. Right? So it's a right triangle as shown by the little red box. That'll be kind of the common thing we see throughout this. In this case, we have a couple of unknowns, x and y. And then we're told that this bottom one here is 9 units long. And then they tell us this piece of information. And fundamentally here, unlike in the last, with the last special triangle, they do need to give me one of the 2 other angles. It's important because these are not going to be equal to each other. If that's 60, that's going to force this one down here to be 30. Okay. So here's where you need to be careful. The side opposite the 30 degrees, and even though it's not written here, it's this other one. So if they explicitly write 30, the side opposite it is going to be my a value. In this case, it wasn't written. It just happens to be the other one. So this guy has to be 30 degrees. Why? Because 60 plus 90 would give me 150. There'd be 30 degrees left over for this corner because it's a triangle. Okay, so that's 30 degrees. Meaning that the side opposite that 30 degrees, the smallest of the 3 angles must be the smallest of the 3 sides, and we're going to designate that A. So A equals my unknown X here in this case. In some cases, you'll be given explicit, like, all right, you'll be given like, this is the actual length, kind of like we're told this one. In other cases, you'll have some algebraic phrase or variable like this. All right, so making my way around, the hypotenuse is double that length. So this is going to equal 2A. And then this one down here, this is the weird one, the one opposite the 60 degrees. This is where I get the square root of 3. A. I usually do these two first, the side opposite the 30, and then my hypotenuse is double that because these ones are a little bit more friendly. This is just the weird one, the one opposite my 60 degrees. Okay, so now I have the following. A is equal to X, 2A is equal to Y, and then square root of 3 times A is equal to 9. And again, I'm going to use substitution here. And depending on what you get, some of these will be a little bit more obvious to what to plug into. So in this case, I know A is equal to X, so I can plug that directly into both of these A's. So let me work first with this 2A. This one will be the easiest one. So I'm going to substitute A for that X. 2 times X equals Y. Not much to do at this point because there's nothing I can really do to solve for either of the variables yet, but this will come in handy later. All right. So now over here, the square root of 3 times A, again, I'm going to substitute that A for X, and that's going to give me 9. All right, so this is going to be very familiar because we just did this for the other special triangle. So let me work through that really quickly, and it will require rationalization, so I'll do that as well. So in this case, I would divide both sides by the square root of 3. I'll get 9 over radical 3. Now, I can't have a radical in the denominator, so here's where I have to do this strategy again. Multiply top and bottom by that same radical called rationalization. And that's going to result in the following. I'm going to get in the numerator 9 times radical 3. In the denominator, the radicals will cancel. I'll be left with just straight 3. These two will end up reducing in this case. So X is going to equal 3 radical 3 here. Officially solved for X. All right, so now I still need to solve for Y, but now I'm just going to substitute in for this X. So in this case, here's where I'm going to substitute that X value in here. So now 2 times that X value, which in this case now is 3 times radical 3, is going to equal Y. Well, this one will be a little bit easier, thankfully, because when I multiply 2 throughout this, the 2 and this 3 will end up multiplying to make 6 radical 3 is equal to Y, and now that one's done. And this makes sense because if this is 3 radical 3, double this would be 6 radical 3. So now I've solved for both variables. If you were asked to round this to the nearest tenth, just briefly showing you the results in the calculator. Let's get the calculator out. I would first start with the square root of 3. For this case, I would multiply times 6. That would give me about 10.4. So 10.4 is approximately the length of Y. And then again, square root of 3 now times 3 should be about half of this. So if I multiply this by 3, about 5.2, which again is half of 10.4, so that makes sense. In this case, X is about 5.2. With that information in mind, just again, sanity checking back here to the original diagram. All right, so if I know this side length is 9, Y we found out to be about 10.4, X was about 5.2. So it makes sense that that times 2 would give me that value. That's a quick sanity check. And the fact that 10.4 is the largest of the 3 sides makes sense because that, again, is this hypotenuse. So those are our special triangles, again, describing the relationship for all 3 sides of a right triangle specifically, but these were 2 unique cases with unique ratios. So that will conclude our section 2 notes. I'll go ahead and stop recording right there.